Right now, a mere 4.2 light years away, close enough to feel like a whisper on the cosmic wind, a small red star named Proxima Centauri breathes fire. Each heartbeat of that ember releases energy on a scale that makes human power plants look like birthday candles. Hundreds of billions of nuclear detonations worth every single second. Circling that glow may be a stony shore, a world in the temperate band where liquid water could pool and linger. Our nearest may be home beyond the sun, and yet between us and that imagined coastline stretches an emptiness so wide that it does not simply challenge engineering. It needles the edges of physics, budgets, and the human spirit. To cross it, we must flirt with speeds that bend intuition, endure tempests of radiation that would char metal, and budget energy as though we were trying to bottle the thunder of an entire civilization. So settle in, breathe slowly, let the night gather around you like a soft blanket. This is a journey to be heard with eyes closed, and as we drift, a gentle note. If this voyage soothes you, quietly tap subscribe and like for Space Historian, so you can rejoin the expedition whenever you wish. No jolting interruptions, just a smooth continuation of the story. We begin with a trick of language. Astronomers call Proxima our nearest star. It sounds like a neighbour's porch light, a friendly glow across a suburban cul-de-sac. That phrasing is a kindness we grant ourselves, because the moment you try to hold the distance in your mind, friendliness drains away and leaves something vast and cold and honest. A light year is not a measure of time, it is a ruler made from light itself. Light, the swiftest thing we know, moving at a pace that would let it lap Earth 7 times in a single heartbeat, needs more than 4 entire years to bridge the space between that red dwarf and your eyes. Imagine those photons. They leave Proxima in a storm of brilliance and then spend over 1,500 nights sailing a black ocean before they strike your retinas, telling you that the star exists at all. Try another picture. Set Earth as a little marble in Manhattan, blue, smooth, slightly scuffed at the edges. Where would Proxima's marble rest? Not New Jersey, not Nevada. Drop it into the middle of the Pacific, where waves churn and no islands break the surface for your thoughts to rest on. Between the two, nothing you can breathe, nothing you can touch. No service stations, no comforting highway signs counting down the miles. Just distances so patient that dust itself becomes a hazard. We like to measure by the speeds we know. New Horizons, the swift arrow that flew past Pluto and sent back postcards from a world of nitrogen ice, hurtles at roughly 36,000 miles per hour. That number feels athletic, triumphant. At that pace, the craft needed 9 years to reach Pluto, an odyssey that thrilled the world. But if you aimed that same arrow toward Proxima Centauri, the estimated travel time would swell to something like 78,000 years. That span is not just older than your grandparents, it is older than the stories your species told when it first learned to trace animals on cave walls. Our finest machines, our tangle of rockets and reaction wheels and precisely machined fuels, stack them all into a single proud timeline, and you still get a crawl. Against interstellar distances, we are ants crossing a stadium, and so the mind reaches for metaphors the way a drowsy hand reaches for a blanket. The space between us and Proxima could swallow 1 million solar systems without letting their edges brush. It is not over there. It is not across town. It is a gulf in which scale itself starts to feel like a dream. The numbers press in. 4 light years, translated from poetry back into arithmetic, lands like a stone. Roughly 25 trillion miles. To write that out, you must march 13 zeros across the page, and still the number refuses to fit in your head. If you tried to count upward to 25 trillion, speaking one number each second without ever stopping to breathe or sleep, not possible of course, but this is a bedtime story, you would be counting for something like 800,000 years. The syllables alone would grind your teeth to dust. Picture walking, 3 miles per hour, a comfortable pace. No detours, no blisters, no hunger. At that speed, the stroll stretches into 9 trillion hours, more than 1 billion years of continuous steps. By the time you took off your boots at Proxima, mountains on Earth would have stood up from the planet's crust and slumped back down into the sea. Continents would have drifted, kissed and parted. Whole families of animals would have emerged and vanished, leaving only fossils and guesses. Driving? A highway cruise would last hundreds of millions of years. You'd watch the sun itself orbit the Milky Way 1.5 times while your tires hummed in a line so straight it might as well be a prayer. Dinosaurs would appear, thunder through forests, and depart the stage twice over during your pit stops for coffee. Even flight, the sleek promise of commercial jets, 600 miles per hour with the world curling beneath your window, shrinks only a little before the abyss. At that clip, you are looking at millions of years in the air. The lineage of Homo sapiens has not yet measured that many birthdays. This is why astronomers trade miles for light years, the way mountaineers trade city shoes for crampons. The terrain demands different tools. Light can circle Earth in a fraction of a second, yet across interstellar space, it crawls. Our minds buckle unless we wrap them in analogies, like ropes around a climber. We learn to balance the poetry with the arithmetic, because both tell a truth the other cannot. But scale is only the first gate in this labyrinth. Suppose, for a dreamlike moment, that we compress the journey in time. Perhaps our engines hum with unheard of power. Perhaps our descendants are patient beyond our understanding. Even then, the act of moving fast through space would follow us into the night with new problems, the way shadows keep pace with the flame that casts them. Consider speed. The elderly Voyagers, those tin-canned messengers launched in the 1970s with their golden records and their hopes, coast at roughly 38,000 miles per hour and have crossed the boundary into interstellar space. An achievement that sounds like myth until you realize it is measured, graphed, confirmed. Aim Voyager toward Proxima and wait, 70+ millennia. Parker Solar Probe went bolder, diving close to the Sun and stealing speed from its gravity until it skimmed through space at nearly 430,000 miles per hour, fast enough to outrun dawn. That is a record born of falling, of cleverness with orbits. Yet even that arrow shot straight needs thousands of years to reach Proxima. Why not just build bigger rockets? Here the universe raises an eyebrow. Chemical rockets, which have carried every astronaut and probe we have ever sent, are squeezing out close to their practical limits. They burn fuel to fling exhaust backward, and the push in the opposite direction moves the vehicle forward. It's elegant and it works for Earth to orbit and across our neighborhood, but when you need to go a meaningful fraction of light speed, the arithmetic turns sly and cruel. Every kilogram of fuel you add to go faster makes the whole ship heavier, which means you need more fuel to push the fuel, and even more to push that, spiraling into absurdity. Propulsion engineers talk about specific impulse, the efficiency yardstick of rockets, and the numbers for chemical propellants, wonderful for launches, just don't stretch to interstellar distances. Even if you built a skyscraper laid on its side, stuffed end to end with the best conventional propellant we know, the payload it could nudge to a respectable fraction of light speed would be tiny. The rocket equation, carved into the sky, says no. Ion drives do better with efficiency. They sip propellant, accelerate ions with electric fields, and whisper their thrust for months or years, adding speed the way a river carves a canyon, not with force, but with time. They are miracles for probes exploring the inner solar system and beyond. Yet their thrust is so gentle that it's measured not in tons but in ounces. To reach 10% of light speed, you would need either centuries of whispering or a step change in technology we have not yet achieved. Beneath all this lies a deeper barrier, the way bedrock lies beneath soil. Taking your energy with you is the problem. The amount you'd need is staggering, even for something as small as a car. If you want to hurry a 1-ton craft to 10% the speed of light, a threshold often treated as the minimum to make interstellar transit feel reasonable, you are no longer talking about fuel tanks. You are talking about the energy output of entire nations over centuries, and that's just to speed up. Newton waits with a ledger at the other end, reminding you that anything that's sped up must slow down if you intend to do more than shoot through Proxima's system like a bullet. Some concepts try to cheat the rulebook politely. Use sails, they say, billow a membrane in a beam of light, or ride the pressure of particles from a star. Catch the wind, but the wind is photons. Or cast out a magnetic net and break against the star's own plasma. These schemes are clever, beautiful in their way, but they live, as of tonight, mostly in papers and laboratories and prototypes, not in starships humming through the dark. Meanwhile, the universe keeps its dangerous weather. Step outside the cradle of Earth's magnetic field and atmosphere, and space becomes a fog of invisible arrows. Cosmic rays, flung from exploding stars and the wrath of black holes, move at near-light speeds. They thread metal like needles through cloth. They don't just pass through flesh, they rearrange its instructions. A crew trying to nap their way across 4 light years would be rocked awake by invisible storms, each particle a micro-hammer blow to DNA. Even mild exposure adds up. A deep space odyssey ladles it out day after day, year after year. A bad solar tantrum, one of those coronal mass ejections that hurls charged particles outward at millions of miles per hour, could spike dose rates high enough to make a crew sick in days. Shielding helps, but the price is weight. Lead is effective but punishingly heavy. Water is kinder. Human beings need it anyway, and can be packed into walls and tanks around sleeping quarters. But to blunt the worst of the radiation, you want thickness measured in feet, not inches. Every extra pound you add to your cocoon multiplies the energy needed to push it. The ship grows heavier to keep its people safer. The engine coughs and demands more fuel. The rocket equation taps its watch again. Even robots and small probes feel the bite. Electronics degrade under constant particle rain. Solar panels lose their shine. Instruments drift out of calibration as months become years. There is no perfect refuge, only trade-offs. And then come the pebbles in the dark. Empty space is not truly empty. It is threaded with grains and flecks. Bits of silicate, carbon, ice. Drift, drift, drift. At walking speeds, they are dust motes in a cathedral. At interstellar speeds, they turn into bullets. 10% of light's pace means closing velocities in the tens of millions of miles per hour. The kinetic energy of even a grain no wider than a hair becomes murderous. A speck of sand, trivial on a beach, would hit with the brunt of a grenade. A pebble becomes catastrophic, a bomb's worth of energy all focused on a point smaller than your fingertip. Steel plates don't shrug that off. They split. Layers ablate. Surfaces erode as though scoured by a storm made of atoms. It is the squared term that does the damage. Double your speed and the impact energy quadruples. Keep pushing and the ledger grows ruinous. Go fast enough and the hydrogen atoms that fill the void, lonely, sparse, start to matter. They carve at the ship's skin like mist made of knives, a gentle, constant sandblasting that never ends. You might be tempted to comfort yourself with averages. Surely there is hardly any dust out there, and that is true by human standards. Interstellar space contains roughly 1 dust particle per cubic mile, which sounds sparse until you calculate collision rates. As a ship aiming for Proxima Centauri ploughs ahead, it doesn't thread a needle through a clean, empty void. It sweeps an enormous volume, billions upon billions of cubic miles, like a snowplow through a winter that never ends. Over stretches like that, chance is no longer a polite probability. It's a near certainty. Somewhere in all those miles, something small and fast will be waiting. Something will strike. Engineers know this, and they plan like mountain climbers tracing routes across corniced ice. One answer is a thick sacrificial shield at the prow, a layered slab whose only job is to be eaten away. But the thicker you make that guardian, the heavier the ship becomes, and mass is a tyrant. Every extra kilogram ripples backward through the design. More mass demands more energy demands bigger power systems. Bigger power systems add yet more mass, round and round. Another answer is to push away what you can before you ever meet it, shaping magnetic or electric fields to nudge charged dust aside. That works for particles that carry a charge, yes, but much of the drifting grit is neutral, indifferent to your clever fields, and it will come on regardless. And the faster you go, the angrier the universe becomes. Bump your target speed from a tentative 10% of light to a bold 20 or 30, and each collision grows from a spark to a blast. A mote becomes a landmine. Impact energies climb into the neighborhood of weapons we dare not test. Even the whisper-thin hydrogen fog between stars, so diffuse you could wander 1,000,000 miles and touch almost nothing, begins to matter. At those speeds it drags, it heats, it bites. Friction with the interstellar medium turns your hull into a stove, the skin warming toward thousands of degrees as you rush through the unseen wind. Dreamers, undaunted, have drawn up another spell. Shine a spear of light into the darkness ahead, a column of lasers sweeping the path clean. Dust that would have struck the bow instead vaporizes yards or miles in front, carving a corridor through the night. But light that powerful is not cheap. The energy to keep such a broom burning would rival the budget needed to push the starship in the first place. You can pay the toll up front, or you can pay it at the gate. The cost, one way or another, returns. This is why so many plans set aside grand, roomy vehicles with parks and corridors and families, and sketch instead something small, nervous and quick. A probe slim enough to dodge, light enough to accelerate, simple enough to shield. Larger craft promise comfort, but the universe taxes comfort at compound interest. And then, above the hum of engines and the whisper of dust, relativity joins the conversation and changes the rhythm of time itself. At modest fractions of light speed, the effect is gentle, like a watch running just a touch slow. At 1/10 of light, the crew's calendar and Earth's calendar would barely part ways, a couple of weeks out of step over a span of years. But push harder, close the gap with light, and time begins to recline for the travelers. At 90% of light's pace, the hours on board stretch, the cadence of days loosens. For someone inside the ship, 2 years might pass while the clocks on Earth tick off more than 4. Move faster still, 99%, and the difference yawns. What takes 4.5 years by Earth's reckoning could feel like 8 months tucked inside the hull. The ship is not just a vehicle anymore. It's a pocket of slower time slipping between the stars. That gift arrives with a price written in human faces. Imagine stepping aboard while your child is new to the world, cheeks round, eyes bright. You return in the flower of your strength, not much older by your count, and find that child grown, middle-aged, with laugh lines and worries you missed. Friends scatter across decades like birds startled from a field. Lovers age apart. The place you left is not only far away, it is also later, remade without you. The crew becomes what poets might call time's exiles, bound not just to a trajectory through space, but to a different current of hours. Relativity complicates the mundane aspects of mission control too. Messages have a way of slipping out of sync. A burst of radio from Earth trudges toward a fast ship and arrives both late and, depending on the ship's velocity, skewed by the slow dance of time dilation. The return message heads home equally out of step. Conversations turn into long-distance letters, their timing elastic, their content always a few chapters behind. As acceleration and deceleration change the ship's frame of reference, the lag morphs and stretches, like a shoreline seen through heat haze. From the crew's perspective, Earth would begin to look sped up. As velocity climbs, the feed from home would seem to flicker faster. Governments rising and receding like waves. Technologies blooming and withering. Landscapes shifting their patchwork. Years would pass in months of shipboard life. Some have suggested using this to our advantage. Launch a crew, let their subjective journey be short and sweet, while the homeworld works for decades, preparing the way for their arrival. It is an appealing puzzle piece if you don't mind those on board being strangers to the world that waits for them. And then there are journeys not of years but of generations. If you cannot go fast enough, you must go long enough. A generational ship promises continuity at the cost of roots. The first voyagers would stand at the viewing port and watch Earth's light dwindle, a blue memory sinking into black. They would understand, down to their bones, that streets and forests and oceans are now stories, not destinations. The ache of that knowledge would be heavy and quiet and unshakable, the sort of ache that visits late at night. Their children would know only corridors and compartments. Sunrises would be LEDs warming through a programmed dawn. Rain would be heard through pipes. Gravity would be a product of spin or machinery. Words like sky, season, and horizon would arrive without the smells and sounds that give them shape. The first time such a person steps onto a planet and sees a cloud shadow run across a valley, what would it do to their lungs, their heart? Some might feel shut in by the ship and shiver at the breadth of a true horizon. Others might find all that space frightening, agoraphobia inverted into awe and panic. In cramped quarters, disagreements don't drift apart, they collide and stick. Small slights can petrify into grudges that outlive their causes. Over decades, politics, beliefs and cultures can branch and branch again until factions are as much inheritance as choice. Resources become levers. A closed world without escape routes is fertile soil for long quarrels. The children of those quarrels, inheriting old maps and wounds, might find themselves fighting for control of systems they do not fully understand, for goals that have blurred into myth. Meaning itself can erode over time. Great-grandchildren might look at a destination charted by someone dead a century and ask the reasonable question, why? Why not turn aside to a nearer star? Why not stop, build, live, and let the future decide? The emotional tether to Earth that steadied the first generation could fray to threads. Mutiny in a spaceship is not a storm on the horizon. It's a change in the air that everyone must breathe. Through all of this runs a subtler pressure. Knowledge must not die. The ship's heart, life support, propulsion, Navigation, farms of green, depends on skills that cannot be allowed to slip. If the person who can repair the CO2 scrubbers falls ill before teaching, if the handful who understand the reactor grow old before students become masters, a quiet failure can snowball into catastrophe. Caretakers carry not only tools, but the dread of being the last who know. We may try to enlist machines as guardians and teachers, artificial minds to monitor systems, to diagnose, to guide hands and perhaps soothe hearts. They might help keep the mission intact, preserve procedures, maintain ritual and purpose. Yet even with tireless partners, the human burden remains: to find meaning, to pass it on, to keep the lights of purpose lit in a place where dawn is a program. All of this assumes, of course, that the ship can keep its people alive, that it can breathe in and out with the precision of a forest and a sea. A true starship must be a sealed world, a necklace of cycles closed so tightly that not a drop is wasted. Air must be scrubbed of carbon dioxide and laced again with oxygen, day after day, decade after decade. Plants can help. Rows of hydroponic leaves drinking light and exhaling what lungs require. But a garden big enough to bear the load is enormous, and gardens are fussy. They want the right light, the right water, the right nutrients, the right temperature. They fail in 1,000 small ways, and each failure needs attention. And the energy cost of turning artificial sun into food is not a footnote. It stands shoulder to shoulder with propulsion on the ledger. Water is both life and armor. You can drink it, bathe in it, wrap your sleeping quarters in it to soften the blow of radiation. But it must move and be filtered and be warmed and cooled. You can reclaim it from breath and sweat and waste, yes. But the machines that do that reclamation have their own appetites and their own tempers. They break. They need parts. They need hands that understand their interior music. Food is not just calories. It is proteins and fats, vitamins and minerals, and the thousands of small compounds that make bodies run smoothly. Some of those can be coaxed from fields of wheat and vats of algae. Others need careful supplementation. Meat, the way we raise it on Earth, is a luxury the ship cannot afford. We invent substitutes, culture cells, rely on plants. But any gap in the balance, the wrong deficiency left to linger, becomes a health problem that does not complain until the bill is due. Earth carries out these recycling miracles with an orchestra of millions of species, a biosphere whose redundancies and feedback loops cushion shocks. A starship's biosphere would be a string quartet, beautiful but fragile. Lose a single instrument at the wrong moment and the music stops. So you stack backups on backups, chemical scrubbers that can shoulder the load for a while, tanks of reserves to drift you through a crisis. Each redundancy improves your odds and weighs you down. Some see an escape in the future. Engineered organisms custom-built to do the work of 1,000 species. Molecular machines that stitch waste back into nutrients with elegant efficiency. These ideas glow with promise, and yet as we speak them tonight, they are still under construction, still more sketch than scaffolding. Even if all that runs smoothly, the ship's conversations with home fade. At first, the delays are mild, like a phone call with a poor connection. Minutes stretch between question and answer. Then it's hours, then days. Beyond the boundary of our solar system, messages begin to feel like postcards from a different era. By the time you are well into interstellar space, a "How are you?" sent from Earth becomes a historical document when it finally arrives. The events it refers to already finished. Advice, troubleshooting, the comforting sense that someone else is watching the gauges with you. All of that thins out and finally disappears. The crew must become their own experts, their own counselors, their own historians. Distance does not just add time, it steals strength. Signals obey the inverse square law, double the distance, and the power at the receiver drops by 4. Stretch those distances to light years, and the strong, clear voice from Mars turns into a whisper skimming the noise floor. The ship's transmitters, sipping from limited power supplies far from the sun, must work miracles to be heard at all. Solar panels lose their usefulness in the cold, faint light beyond the outer planets, and other power sources must carry the load. Blackouts, partial silence, long pauses. These become part of the crew's weather. So the ship learns self-reliance. It must fix itself, comfort itself, teach itself, and decide for itself. Every problem encountered is a problem to be solved before the echo of a question can return from Earth. And then, finally, the destination's light grows from star to star with complications. Proxima Centauri, our neighbour not by friendliness, but by proximity, reveals a personality that is all storm and scar. Red dwarfs live long, longer than we can easily say, sipping their fuel so delicately they could outlast our sun by factors of thousands. But they are not gentle elders. They flare, they leap, they rage. Proxima has been seen to brighten tenfold in minutes, tantrums that throw out radiation as if someone had torn up the rulebook on safety. These flares whip charged particles to ferocious speeds, filling the space around the star with invisible knives. Compared with that, the radiation of interstellar travel begins to look like drizzle before a hurricane. A ship that arrives under one of those outbursts is a deer stepping onto a highway at midnight. The doses inside the hull could spike to levels that ruin electronics and sicken, even kill human beings. Even if there are no people aboard, the ship's nerves, its circuits and sensors can be stunned or burned into silence. Proxima b, the planet that tempts us with the word habitable, circles its star from a radius so tight it would make Mercury blush, about 4 million miles. There is no safe distance cushion there. The planet stands where every flare's first hammer blow lands. Over billions of years, that means winds of particles strong enough to sandblast away atmospheres. If there was once a sky to breathe, it may have thinned, then fled. Under such a star, the ground could be a palimpsest of radiation scars. Wrap a star like Proxima in its magnetic fields, and you get belts of trapped particles. Van Allen belts, but swollen and sharpened. A ship slipping into that system would need to thread those belts carefully, reading and avoiding and hoping, all while the star's temper changes without warning. And because Proxima b is likely tidally locked, one face may roast in perpetual day while the other freezes under an eternal night. Life, if it found a way, might cling to the ring of twilight between inferno and ice, where the star is forever just at the horizon. Timing becomes part of survival. Flares are not polite enough to arrive on a schedule we can consult 4 years ahead. You launch under quiet skies and arrive under a tempest. Or worse, you thread into orbit just as the star twitches, and everything you have carried so far meets a wall of particles with no mercy in it. Mission planners can model, monitor, predict. In the end, they must also accept that some dice will be rolled where human hands cannot reach. If this soft, steady voyage keeps you company in the dark, drift with it. And when you're ready, gently subscribe and tap like for Space Historian, so the next chapter finds you again without fuss. And still, for all our care, for all our learning, some arrivals will simply be unlucky. The flares will not care. They bloom and fade on their own clock, and any ship that meets them meets a force beyond human control. The dangers waiting at the destination are only the last breakers on a much rougher sea. Before any ship can even dream of arriving in the Proxima system, It has to move, truly move, through the dark. And that means choosing a way to push against nothingness, a way that presses up against the edges of what physics will allow and what engineers can build without their hands shaking. One of the gentlest ideas is also one of the oldest. Stretch a mirror to the sun and let light do the work. Solar sails don't gulp propellant or spit fire. They lean into sunshine. Photons carry momentum even though they are massless, and when they bounce off a reflective sheet, they give it a feather's nudge. On Earth, a breeze that soft would not trouble a spider web. In orbit, with no air to fight and no friction to steal the push, that whisper can become motion. The trick is patience and size. To get meaningful acceleration, you want a sail so broad that a city could hide in its shadow, yet so light that the numbers on a scale barely notice it's there. That is why the materials must be gossamer thin. Films measured in mere atoms, graphene lattices, ultralight polymers engineered to gleam, promised like silver leaves. You want reflectivity without heft, stiffness without thickness, but a membrane that light is a thing of delicate moods. Micrometeoroids will pepper it with pinholes. Ultraviolet light will roughen and weaken it. Thermal cycles will tug and relax it until any fold becomes a fault line. We have flown sails a few hundred feet across, modest kites by comparison, and even those demand choreography to unfurl cleanly. Scale that up to tens of miles, and you are attempting origami with a skyline. The sail must blossom perfectly far from home, hold its shape for decades, and shrug off an occasional grain of sand, travelling at a fraction of light speed. And time is not on the sail's side. The sun's pressure fades with distance. That soft hand that helps near Earth is barely a touch past Mars. A pure solar sail would spend months or years easing outward, gathering speed while the light is strong, then lock in that velocity and coast the remaining light years. Elegant, yes, but slow enough that generations would count the journey rather than calendars. So the dream shifts. Keep the sail, but replace the sun with a man-made star. If Earth could fire a narrow, unblinking beam, lasers arrayed in their thousands, synchronized into a single lance of light, we could push a sail long after sunlight weakens. The math is intoxicating. No fuel on board, just a steady shove from home. But this grace comes with knife-edge demands. A beam must be held on target with accuracy so fine it makes a surgeon's hand look clumsy, and it must stay there across millions, then billions of miles. The sail, for its part, has to look directly into that brilliance without flinching, keeping itself aligned to within fractions of a degree or risk being flipped, torn, or simply waved off course. One software hiccup, one twitch in the optics, one torn panel, and the craft becomes a drifting leaf. The beam spills into emptiness, and the mission dissolves without drama. Still, there is a quiet, ruthless advantage to light sails that nothing else can match. They don't have to carry their own energy. When every gram hurts you, not having to haul propellant is a relief you can feel in the equations. Other engines make a different bargain. Ion drives trade snarling thrust for unheard of efficiency. They take noble gases, xenon is a favourite, strip electrons away, and then fling those ions out the back using electric fields. The exhaust speeds are astonishing, orders of magnitude beyond chemical rockets. Every ion that leaves gives the craft a tiny recoil. The push is so gentle you could trap it with fingertip and thumb, and yet if it never stops, if it whispers day after day, month after month, the speed builds like interest in a patient account. A ship with ion engines doesn't leap away from Earth. It spirals outward, a slow corkscrew that becomes a long, quiet sprint. The catch is power. Those electric fields want electricity. Kilowatts at first, then megawatts. And if you dream of fast interstellar flight, perhaps more. Missions like Deep Space One once spread solar panels as wide as small courts to feed a single thruster that could barely press down the weight of a slice of bread. To scale ion propulsion up to the point where years become decades instead of centuries, you start sketching power plants the size of city blocks, vast solar farms near the sun, or nuclear reactors strong enough to glow with their own problems. The physics smiles, the engineering frowns. Reactors must run for decades unserviced, bathed in radiation, their waste heat managed in a vacuum where dumping warmth is harder than you think. Solar arrays fade as light thins. Beyond Jupiter, the numbers grow unforgiving. Even so, ion engines flirt with the theoretical limits of how efficiently a rocket can turn energy into motion. They waste little. They ask you for patience and electricity, and in exchange they give you speed that a chemical rocket can't buy, no matter how much fuel you pour into its belly. 10% of light's pace may be reachable with heroic designs. 20% is a taller mountain. Eventually, the wall of relativity looms, and ions, for all their elegance, start to look like shoes too soft for a hard trail. If you want blunt force, you can borrow the most concentrated energy humans have ever learned to unleash. Nuclear explosions. The nuclear pulse stream is audacious in its honesty. Don't pretend the engine is gentle. Accept that you are riding shockwaves. A stout steel plate, your pusher, faces backward. Bombs the size of suitcases drop, detonate at a careful distance, and each blast hits the plate like a cosmic hammer. Between plate and crew, an intricate suspension of pistons and shock absorbers takes the punch and spreads it into a shove. Do this not once, but hundreds, then thousands of times, and the ship gathers speed the way a drummer gathers rhythm. On paper, the numbers are persuasive. A single detonation equals mountains of chemical propellant. Chain enough together, and you are genuinely talking about fractions of light speed with the sort of payloads that look like science fiction interiors. Habitats, laboratories, shielding, provisions, everything you'd need to travel not as a dart, but as a caravan. Orion, the name given to the most studied version, got far enough along that engineers worried about plate materials, ablation layers, and the chemistry of bomb casings. It is less fantasy than a plan waiting in a locked drawer. Open the drawer and a tangle spills out. Pusher plates must not pit or melt or crack. The suspension must not jam or snap. The timing must be perfect, because sloppy is catastrophic when the propellant is a sun in a box. Each blast breeds radiation. Flash, neutrons, electromagnetic pulses that wants to blind your electronics and salt your ship with radioactivity. The crew would live inside a fortress of shielding, and that fortress is heavy. Then there is Earth's voice on the matter. Treaties, test bans, the moral weight of lighting nuclear fires in the sky. Even lofting such a craft from the ground would turn launch sites into pariahs. The environment, the politics, the fear, each is a cord around Orion's ankles. Yet it lingers in the imagination precisely because it is one of the very few ways we know to push something big, something human-sized, to speeds that turn starflight from a wish into a schedule. Beyond even that, beyond bombs, sits a different grail. Antimatter. Where nuclear fission and fusion convert whispers of mass into energy, antimatter turns the whole song into fire. Matter meets its mirror, proton to antiproton, electron to positron, and the pair disappears, their mass reborn as energy in a perfection that makes engineers dizzy. The equation is famous and merciless. A tiny amount of annihilated mass equals an astonishing amount of energy. Exhaust could, in theory, be driven to velocities that flirt with light itself. Fuel mass plummets. journey times begin to look like chapters rather than epochs. But to fill a tank, you first have to make the fuel. And our machines, great rings of magnets, caverns of superconducting coils, make antimatter in snowflakes, not shovelfuls. Every particle costs a king's ransom in electricity. At current rates and efficiencies, a single gram would drink the output of nations for years upon years. Then you have to keep it. Antimatter cannot touch the vessel that holds it. It must hover inside electromagnetic cages in a near-perfect vacuum, waiting without touching for as long as the mission endures. If a trap fails, if the bottle hiccups, the resulting spark is final. Even when everything works, annihilations produce radiation harsh enough to demand walls of shielding between the engine and any crew, a heavy wall that steals back the advantage you just won. And all the while, the security risk sits in the background, cold and inarguable. Grams of antimatter are weapons as much as propellant. The world would have opinions and not mild ones. Even so, within the library of propulsion ideas, antimatter sits on a high shelf, not because it is easy, but because if someday it becomes practical, it may be the first tool that makes relativistic a word engineers use at meetings instead of poets at midnight. There is another cleverness. Do not carry fuel at all. Eat as you go. The Bussard ramjet imagines a ship with a magnetic mouth thousands of miles wide, a scoop that gathers the thin hydrogen mist between stars and funnels it into fusion engines. The faster you fly, the more atoms you catch. The more you catch, the stronger your fire. The stronger the fire, the faster you fly. A virtuous circle that ends in speeds worth dreaming about. In a universe where space is never truly empty, this is a fisherman's idea. Net the river while you travel it. But the river is sparse. A cubic centimetre of interstellar space may hold only a single hydrogen atom on average. To comb a meaningful stream, your magnetic scoop must be extravagant, its fields arcing and curving across distances that are hard to draw to scale. Those fields want power, and lots of it. The fusion that would feed them, in turn, asks for temperatures and pressures that we have, so far, only cajoled into existence inside stars and short-lived experimental machines. And there is a trick within the trick. To net enough atoms, you must already be moving very fast, which puts you back at the start of the maze. Worse, as detailed models have shown, the very act of ploughing through the thin hydrogen can create drag that cancels out the thrust you gain from burning it, turning your grand engine into a brake that slows you until there is nothing left to burn. Ideas rarely die, they evolve. Variants appear, different magnetic geometries, catalytic cycles, hybrid stages that use carried fuel to spin up to speeds where scooping becomes profitable. Each is a sketch pinned to the future. While the grand ships argue with physics, another path skirts the edges. Abandon bulk, make the traveller tiny, make the trip fast, and accept that the first ambassadors across the dark will not have heartbeats. The breakthrough Starshot proposal is exactly that kind of audacity. Build an array of lasers on Earth, a field of light mills with combined output in the gigawatt range, and fire their beams into the sky as one. At the focus waits a fleet of wafer-thin craft, each no heavier than a dragonfly, each carrying cameras, sensors, a brain so small it could sit on your fingernail. Unfurl an ultralight sail behind each one, catch the torrent of photons, and let the craft leap. 20% of light speed is the target. At that pace, Proxima is not 1,000 human lifetimes away. It is 2 decades of calendar pages. There are, naturally, tall demands. The ground array must hold its beam steady across the breathing atmosphere and the jitter of Earth. It must coordinate its countless emitters as if they were one mirror. The probes must endure brutal acceleration, and the first sharp minutes of dust strikes at impossible speed. Communications must be stingy and brilliant to whisper home from 4 light-years away with power stores measured in thimbles. But the prize is clarity. No propellant to carry, no heavy shielding, no farms and families, only instruments sprinting into the dark, then braking not at all, but flashing through the Proxima system in an eye blink to snatch pictures and spectra and whatever science a handful of grams can hold. If you're floating with this story and want its next quiet chapter to find you again without fuss, gently subscribe and tap like for Space Historian. It helps the voyage continue, softly and on time. To make that sprint possible, the beam must be held like a needle pointed across a continent seen from the moon. Alignment cannot slip. The sail cannot flutter. Even a brief twitch can turn push into tumble. And so the plan ends, at least for now, with the image of Earth's bright lattice of light turning night into a launch pad, its photons reaching up to brush a mirror the size of a postage stamp, miles above the ground, as these laser arrays would focus their energy into tight beams capable of pushing small spacecraft equipped with ultra-lightweight solar sails. Picture a lattice of light the size of a city switching on in the desert night, thousands of lasers breathing in unison, and a drift of glimmering specks riding that radiance like dandelion seeds in a sunbeam. In minutes, the beam pours momentum into each speck until it is no longer a speck but a streak, an ember thrown from Earth at a speed that would make every past mission look still. This is the heart of Starshot. Not a single proud ship, but a cloud of nearly weightless scouts, each no heavier than a paperclip shaved to a sliver, each no bigger than a postage stamp when its sail is folded away. Inside those gram-scale travellers, a wafer of cleverness, cameras as thin as eyelashes, sensors pressed flat as leaves, a whisper of onboard memory to bottle what little light Proxima will lend them when they flash by. Fabrication lines borrowed from the world that etches circuits by the billion could, in principle, stamp out fleets of such scouts for the cost of one traditional mission, trading mass for multiplicity, risk for redundancy, lose a few, send more. The void becomes a place for swarms, not flagships. Acceleration for them is not a gentle drift. For a handful of breathless minutes, the beam shoves with a harshness that would pulp a human and tear a normal spacecraft to tatters. But tiny things endure what large things cannot. Their sails, so thin you could read a love letter through them, catch the laser like a hawk's wing and must never flutter. Orientation is everything. A tilt the width of a thought, and the beam slides off. The probe tumbles. The sail rips. The mission goes dark. Guidance, therefore, must be exquisite. Software must see the jitter of air in the beam's path, the roll of Earth beneath the array, the minute flex of a sail that weighs almost nothing, and correct every millisecond or fail. From the ground, the aim must be truer still. Hold a bright pinprick on a target smaller than a fingernail. Keep it there as the target leaps from rest toward a fifth of light speed. Compensate for shimmer, for spin, for the slightest mechanical shrug. A pointing error finer than a human hair at arm's length could send the beam wide. In this ballet, both partners, the sail and the sender, must never miss a step. There is no braking burn at the far end. These scouts don't carry tanks or engines to claw back speed. They will thread the Proxima system in a blaze, not a loiter. Hours of science after decades of flight. Everything must be automatic. No one will answer their questions in time. The nearest greeting would arrive years late. Each craft must wake itself, aim its gaze, harvest what photons it can, decide what matters, and compress it into a squeak of a message. communication becomes a prayer. A chip can't haul a transmitter with the lungs to shout across 4 light years. It can only murmur. On Earth, radio eyes must grow vast and patient, raking the sky for signals 1,000 times dimmer than what we can comfortably hear today. We must be ready for the possibility that the transmission hardware which slept in the cold for 20 years will blink once and die. We must be ready too for the miracle, a scatter of bits arriving from the dark, stitched back into a blurred coastline of another sun's world. For all its pains, this is the most near-term bridge we have, from us to there, built not of hulls and habitations, but of speed and number. If this kind of quiet, careful voyage keeps you company as you drift towards sleep, tap subscribe and like for Space Historian, so the next chapter can find you softly, right where you left off. Human voyages demand a different mercy. If you cannot make the miles less, perhaps you can make the hours shorter, inside your own skin. Suspended animation sounds like myth until you remember winter. Bears and ground squirrels lower the flame of life and sleep through a season. Hearts thudding slowly, cells wrapped in chemistries that ward off frost and hunger. Medicine has borrowed a faint echo of that trick. In operating rooms, bodies are cooled for hours to protect brain and tissue while surgeons work. It is not hibernation. It is a pause button with a timer. Stretch that pause to decades and the problems multiply. In true torpor, metabolism falls tenfold or more. Oxygen needs dwindle. Food becomes an occasional accounting instead of a thrice daily demand. But in humans, the pathways are only guessed at. We can point to signals and hormones in animals that say, "Sleep now," to the body's engines. We can name proteins that shield cells when temperatures fall. Translating those notes into our own physiology, safely, reliably, for years, that's a score no one has yet learned to play. Even if we could pull the curtain of sleep over a crew, the stagehands behind it would need to be tireless. Machines would feed, clean, monitor and adjust. They would notice small emergencies before they matured. They would be the nurses, the dietitians, the intensivists, and the watchstanders for a ship of sleepers. They would also need to be perfect, or close enough to perfect that the imperfections never stack into catastrophe. Cold changes blood. It goads the heart into rhythms you don't want. It thickens the fluids that should slip. It invites clots to wander. Therapeutic hypothermia today is a dance done with vigilant hands and eyes. In interstellar torpor, there would be only the ship. Waking is not a shrug either. Bodies that have floated in place for years must relearn weight and effort. Bones leach calcium without load. Muscles unknit when they're not asked to work. Nerves and senses sulk. To rise from a cradle after decades and be ready for first steps on alien ground is a rehabilitation problem so large it becomes a mission in itself. Some schemes imagine never fully crossing into sleep, keeping crew members in a twilight of awareness, slowed but not stilled to ease the climb back to waking. Others imagine cycles, months down, weeks up, sharing the watch between hibernations. Or perhaps no one sleeps because no one boards. Machines don't miss their children. They don't require water, air, or laughter to be whole. They can soak up radiation that would unspool human DNA, and if one fails, you send 10 more. Already, our ships are part robot and part promise. Mars rovers choose routes and targets. Quiet brains thinking under thin skies. Scale that autonomy outward and forward, and you could have explorers who never call home except to report what they've learned. But true independence is hard. Today's cleverness is narrow, superb at a task, lost outside of it. An interstellar mission would be an odyssey of the unexpected. Systems would redden and go silent. Dust will not care about your schedules. A faint star will flare. An AI would have to make choices without waiting 4 years for advice. Choices about risk, about which data to save and which to let go, about how to salvage a dying instrument, about whether to dive closer for a better look or hold to a safer, duller path. In those choices, where none of the answers is obvious, ethics lives. We would need to teach it not just to think, but to care what it thinks with. Robot ships bring another gift: lightness. Strip away the habitats and galleys, the gardens and water walls and sleeping berths, and mass drops by orders of magnitude. Every ton you don't have to protect from radiation or feed 3 times a day is a ton you can devote to speed or spare entirely. A machine can be armoured where it needs it most. It can be built from materials that would poison a person but please an engineer. Electronics will still age under cosmic rays, but redundancy, like a braid, can keep strength after strands snap. If we insist on carrying people and their weathers with us, we soon sketch arcs instead of arrows. A viable generation ship is not a cabin with a view. It is a floating commonwealth. To keep culture alive and genes diverse over centuries, you don't send a family, you send a town, and more likely a city. Forests under domes, lakes that feed fields, schools and courts, workshops and theatres. The whole becomes horizon, the ship becomes world. Gravity must be made where it cannot be found. We have learned what weightlessness does when it lingers. Bones thin, hearts laze, balance systems grow petulant. The simplest fix is spin. Build rings so large that their inward push feels like a down. But size and strength wrestle here. To make 1G, without making people woozy with Coriolis effects, diameters stretch to miles. The outer skin strains under forces that would rip steel like cloth if the wrong vibration sets in. We speak hopefully of carbon nanotubes and other wonder materials, of manufacturing that can lay them out in spans measured by city blocks, not lab benches. For now, it is a promise more than a plan. Inside, the ecology must be almost perfect. Earth's biosphere is an orchestra of millions, with redundancies layered over redundancies. A ship's garden is a quartet. Lose the pollinators, foul the microbe mix, let a nutrient cycle drift out of balance, and the feedbacks that should cushion you instead amplify trouble. There will be backup systems, chemical scrubbers to yank carbon dioxide when the green rooms falter, reservoirs to drink from when the rivers stall, and every backup adds weight, complexity, points of failure, and the steady hum of maintenance tasks that never end. The people will change. How could they not? Languages shift in less than a century even with neighbours all around. Aboard a closed world, dialects would curl and diverge like vines. Customs would grow to fit corridors and ration schedules. Politics would harden around air, water, heat, and the levers that control them. The children of the second generation might honour a destination they've never seen. The great-grandchildren might not. Their myths could turn the mission into something else entirely: holy pilgrimage, or exile, or a duty owed to ancestors, or a mistake to be corrected. And through all of that, they would need law, story, art, science, patience, and a way to handcraft and purpose from old hands to young without the chain snapping. Then there is the bill. A ship that can cradle 10,000 souls across light years is not a line item. It is an economy. Mines must bite deeper than any before. Foundries must pour rivers of new metals. Factories must learn to braid materials we have so far met only in journals. The price tag climbs out of billions into trillions, and then has the indecency to keep moving. Perhaps no single nation could even attempt it. Perhaps it would take a chorus of flags and languages, a treaty that outlasts a dozen governments, a commitment measured not in election cycles but in eras. Why spend so much? Insurance is a quiet word for fear and foresight. We buy it against house fires that almost certainly won't come because the small chance of ruin is a weight we cannot carry. On the scale of species and worlds, the list of low probability, high-cost events is not short. Rocks wander through space. Sometimes they do not miss. Supervolcanoes sleep shallowly. Stars can spit gamma that burns not skin, but atmospheres. We are busily inventing risks of our own too. Cleverness without restraint is just another hazard. Against that backdrop, the idea of seeding other skies so that humanity has more than one cradle begins to look less like extravagance and more like prudence. The trouble is that the graphs we use for money bend under this kind of weight. Returns on investment love quarters and years. They grow confused by centuries. The knowledge and resources gained by planting a flag among the stars may take lifetimes to flower, and the people who water them will not be the ones who first wrote the checks. Classic accounting falters where grandchildren reap harvests from fields their great-grandparents never saw. Cooperation, then, becomes not a platitude but a requirement. No single treasury, no single workforce, no single will seems enough for projects that span centuries. The politics of such long commitments are their own engineering problem. How to keep a promise alive across generations. How to share sacrifice and credit. How to settle disputes without shattering the hull. International compacts would need to be as robust as pressure vessels and as carefully tended. The patience of a species would be on trial. And still, beneath the numbers and the treaties, the logic circles back to survival. That we would even consider building cities that sail is evidence of what waits below the horizon of years. If the cost is unimaginable, what it buys is immeasurable. The question becomes not just whether we can afford to go, but whether in the long run we can afford not to. Since no single nation possesses the resources needed to build generation ships or advanced propulsion systems, the political challenges of maintaining international cooperation for century-long projects rival the technical challenges of interstellar travel itself. Ambitions this large don't fail only in laboratories or launch pads. They falter in parliaments and boardrooms. Budgets shift with headlines. Leaders change. Priorities flip. Alliances cool. An interstellar program must survive not just physics but politics, not just engineering but elections, a single veto, a fiscal winter, a conflict in the wrong region, and the long arc to another star can snap like a brittle thread. Private fortunes may step in where public patience thins. There will be founders who stare at balance sheets measured in trillions and decide that the greatest moonshot isn't the moon at all. It's the first ember of human life lit under a red dwarf's dawn. A handful of visionaries could stake the opening moves. Prototypes, beam arrays, seed factories in orbit, the first trail of robotic scouts. Philanthropy can light the fuse, but a city that sails between stars can't be crowdfunded. Generation ships and deep time propulsion push past the reach of even the widest individual purse. In the end, the ledger balances on a single question. How much is our species worth to itself? While we argue over cost and courage, Proxima b waits. No gentle twin, but a study in extremes. The planet is held by its star's gravity the way a face turns always toward a hearth. One hemisphere locked in unending noon, the other in a night that never softens. Imagine a world cleaved by temperature, rock simmering under a furnace sky on one side, an abyss of cold on the other, where air itself could freeze and fall as snow. Between them lies a narrow ring of permanent dusk, a twilight belt where maybe, only maybe, water could pool and linger. Set your boots on the day side and they'd soften like wax. The air would be stripped thin by flares and stellar wind. The ground might ripple with lava, the light harsh as a welder's torch. Set them on the far night and they would crunch on frozen gases. The thermometer would sink towards silence. Your breath would be a brief cloud and then a memory. In the grey band between, the Terminator, the weather would never rest. Pressure differences would drive the atmosphere in a colossal constant circuit. Gales would roar from heat to cold like a planet-sized lung, sandblasting rock, carving dunes, pummeling any lander that dared to lower its legs. Above, Proxima itself would tantrum, sudden flares lancing the sky, radiation storms that neither calendar nor caution could predict. Any life that hoped to endure there would need to hide, under oceans, under stone, surfacing only between tempests. If there is a magnetosphere at all, it's likely a thin shield compared to Earth's strong cloak. Without it, the star's wind would gnaw at the air for eons, atom by atom, until the planet wears a mask of atmosphere rather than a face. And yet, in all its danger, Proxima b remains a kind of North Star for our imaginations, not because it is kind, but because it is close. Closeness matters when every mile is heavy. Before any vessel arrives, a message could. Radio moves at light speed, a courier we already command. We could send first hellos years ahead of any probe. Think of beams launched from Earth's great dishes. Not just greetings, but a braid of mathematics, primes, geometric ratios, harmonics, patterns that any science would recognize. We could tuck in the bones of our knowledge, the ways we count, the shapes we draw, the chemistry we breathe. In crafting such a message, we learn humility. How do you paint blue for eyes that see in a spectrum shifted from ours? How do you hum minor key to minds without ears? The act of translation becomes a mirror held up to our own assumptions. Our transmitters can already shout far into the dark. The most powerful arrays we've built have reached for planets and craft at the edge of our system. Mirror them at Proxima and, in principle, the exchange is within reach. Timing then becomes a piece of artistry. Signals sent today arrive a little over 4 years later. If fast probes follow, their blur through the Proxima system could occur within the same historical breath. Redundancy helps. Repeat the message, vary the bands, change the polarization, so that noise and weather in an alien sky have fewer ways to garble our intent. In a cosmos where storms happen, persistence is its own language. Of course, to shout is also to be heard by whoever is listening. The beacon that says "we are here" says something about our reach and our tools as well. Prudence and hope must share the drafting table. Prudence is the quiet principle behind redundancy in everything we send. The distances are so great that a single broken hinge, a single unlucky pebble at relativistic speed, a single bug in code left unpatched can erase decades and fortunes. So you hedge. Don't send one arc, send several on staggered trajectories with different architectures and launch dates. The cost multiplies, yes, but so does the chance that at least one thread of the tapestry survives to the end. Aim more than one star too. If Proxima b is a dead ember or a murderous storm, let missions also ride toward Tau Ceti. Wolf 359, Gliese 667c, an armful of nearby waypoints, so we're not betting the entire future on a single coin toss. Diversity in propulsion is another kind of insurance. Let one team perfect ion engines that murmur for years. Let another refine nuclear pulse designs that kick and leap. Let a third polish cell membranes so thin the sun can push them. Let a fourth chase fusion's white whale. If one axis of progress jams, another might turn. Meanwhile, shrink your scouts. Robotic precursors sent by beam could be our eyes and weather reports, arriving in decades, not millennia, tasting atmospheres, mapping fields of radiation, proving or disproving habitability where theories can only guess. Between stars, the silence is not just lonely, it can be absolute if we don't build ladders of listening. Relay stations, nuclear-powered sentinels with dishes like lilies, could stand along the long road, stretching our hearing, ferrying whispers from ship to earth and earth to ship. A net of these nodes, anchored in deep space, would let a dozen missions talk to each other as well, sharing cautions, discoveries, course corrections, a convoy in the dark. Inside the ships themselves, time becomes weight. Parts fail on the scale of years. Bolts back out, lubricants dry, electronics brown in radiation and age. You can't pack a warehouse of spares for centuries. So the ship must be its own factory. 3D printers that handle not only plastics, but metals and ceramics. Tool arms that can place components as precisely as any clean room. Smelters that sip scrap and recast it. The raw feedstock can be carried, traded, harvested from small bodies met along the way. Every part you can make is a part you don't have to beg a distant Earth to send. Beyond even relays and repairs lies the final redundancy. Many homes, not one. The way to keep a species from falling to a single blow is to make sure no blow can reach all of it. The first colony may fail to drought or bad soil, or the unseen pressure of isolation. The second might learn from the first. The third may become something new and teach the others. Survival is not a bunker, it is a branching. Why branch at all? Because time is patient and impartial. The earth is beautiful and mortal. The skies above it hold old dangers with young faces. The sudden stone from the dark, the ash of a hungry mountain. Radiation scythes from distant tantrums. The risks of our own cleverness deployed without wisdom. History teaches in strata. The dinosaurs ruled longer than our species has existed and were undone in an afternoon. We are here because the story didn't end there. To make sure the next plot twist isn't our last, we seed the future in more than one field. The road to that future doesn't just protect, it transforms. Technologies forced into being by the need to keep a closed world alive for centuries would boomerang home. Power systems efficient enough to hum for decades without servicing would change cities. Materials tough and light enough to spin mile-wide rings would upend construction. Closed-loop ecologies perfected in cylinders would rewrite agriculture and waste. Autonomous systems that can diagnose, repair, teach and govern in isolation would reshape industry and medicine. The habits of mind demanded by interstellar projects, thinking in centuries, valuing resilience over immediate gain, could cool hot politics, widen narrow debates, and teach economies to save for grandchildren they'll never meet. Perspective is its own technology. Look back at Earth from a light year away, and borders shrink. Fights over line on map and moment are bathed in the same small blue. Problems that seem insoluble might yield to tools forged for starships. We'll need those tools, not just to go, but to remain worthy of going. There is a ledger here as well, the economics of we. Early on, there will be no profit statement that pleases quarterly reports. Returns, if you insist on the word, will be measured in avoided disasters, in knowledge grown, in the endurance of stories and languages not yet spoken. Over centuries, as daughter worlds rise, they will pay back the investment 100 different ways, resources and ideas flowing along routes of light and patience. But those who plant the first seeds will do so, knowing they will never taste the fruit. That too is part of the graduation. And graduation is what this is. To step from a single planet to the open galaxy is to move from adolescence into something more sober, more spacious. It asks for better versions of us, more cooperative, more far-sighted, more curious and careful at once. The cost is as high as the sky. The alternative empties the ledger of meaning entirely. We have already shown a talent for rewriting the impossible into the ordinary. We sent metal to every planet in the sun's garden. We took pictures where no eyes have ever looked. We taught stones to think, and they in turn taught us. When the fire was new, we huddled and told stories to keep the night from feeling too large. Now the night is larger, and we're learning to tell better stories. So the path to Proxima is a curriculum. Radiation that punishes carelessness, energies that beggar nations, silences that demand autonomy, distances that mock impatience, climates that will scald and freeze in the same heartbeat. Every mile reveals another exam, and yet threaded through every problem is opportunity. To learn, to unite, to lengthen the horizon across which we plan. Out there, 4.2 light years away, a red dwarf burns with the condensed fury of ages. Around it turns a world that could become not a paradise, but a foothold. Between here and there lies enough emptiness to swallow 1,000,000 solar systems, and enough possibility to write a future that stretches beyond the lifespan of seas. This is more than travel. It is the attempt to let consciousness, craft, and love outlive their birth world. If this quiet voyage helps you drift, and you want to follow every step we take into that larger night, subscribe and tap like for Space Historian. Gentle signals that keep this story funded and flowing. The work ahead is cathedral work. Many hands, many years, stones laid by those who will never kneel in the finished nave. It is also lifeboat work. We do it so that the universe cannot end us with a shrug. The technology will be hard, the politics will be harder, the patience will be hardest of all. But somewhere along the way, a beam of radio will arrive at Proxima and say hello before we do. Somewhere along the way, a wafer-sized probe will streak through a pale ring of dusk and snap the first true picture of an alien shore. And later, much later, children will step out under a red star and throw stones across thin water and laugh. Make sure to subscribe and hit that notification bell for Space Historian, because this journey is just beginning and the next impossible destination awaits just beyond the edge of our imagination.